You got it? I'll begin. Heavenly Father, we thank you for this day, and just thank you for these students. Pray you help them as they're studying for this class, that they spend all their time on this class so that they can do well, and ignore all their other classes, because they don't matter. We know it's true. We pray that I'd be able to focus today despite the unpleasant and ridiculous temperature in this room, Lord. You know my prayer. Amen. All right. Oh. All right, so let's talk about some algebra. Lecture 33, number theory. Okay, so let me start out with sort of a benign observation about complex numbers, all right? So you guys know, if we have z1 equal to x1 plus iy1, and if we have z2 equal to x2 plus iy2, right? You know you can construct the conjugates of these, right? Z bar 1, x1 minus iy1, z bar 2, x2 minus iy2. If you're coming in late, yes, you, Mr. P. Maybe it's just on time, I don't know. I gave another day to work on the homework, but I must have it before the help session tomorrow because I'm planning to discuss the solutions to the homework you're going to turn in today tomorrow, so there's that. Now, there's this wonderful thing that if z is equal to z1 times z2, right? In other words, z is equal to what? x1, x2 minus y1, y2, right? Plus I times x1, y2 plus x2, y1, or however you want to write these, right? Did I do it right? I sometimes mess up the multiplying. Let me think about it for just a second. Right? Then you know that the modulus of z, and then we've got this thing, the modulus of z squared is equal to what? What's it equal to? Well, it's equal to the modulus of z1, z2 squared, right? But we've got this cool property for the modulus, which is that the modulus of z1 times z2 is the modulus of z1 times modulus of z2, right? And if you square that, well, then we get the squared moduli as well. So what does this tell me? This tells me that if I look at, let's look at this way. If I look at x1 squared plus y1 squared times x2 squared plus y2 squared, what do I get? So this is x1 squared plus y1 squared, right? And this is x2 squared plus y2 squared, right? Because the modulus is the distance, and the square of the distance is just the sum of the squares of the Cartesian components of the complex numbers. So we get the product of x1 plus y1 squared times x2 plus y2 squared equals to what? The sum of two squares, right? The sum of this thing. Right? And this right here, what's this called? Do you guys know? This is known as the two-square identity. Right? What it shows is that if you take the sum of two squares and you multiply them, you can rewrite it once more as a sum of two squares. Now, you might go and ask the question, can you do this for three things, right? Or can you do it for, can you do it for three things? And the answer is no, you can't. But you can do it for four things. There is, in fact, a way of multiplying x1 squared plus x2 squared plus x3 squared plus x4 squared times y1 squared plus y2, I'm violating my notation. I hope it's okay, y3 squared. I mean, I'm changing my notation. That's here. you can rewrite this as a sum of 4 squares. This is called the 4-square identity. But yes, it's not possible to do it for 3. There's also an 8-square identity. All right. So where's this coming? I mean, where's the 2-square identity coming from in some sense? It's what? Yeah.
Is there a 16-square identity?
I don't think so. I think it's just 2, 4, and 8. And it has to do with, this is actually Hurwitz's theorem, I think, stated in an unusual way, I suppose. But, I mean, this is basically coming from the existence of complex numbers, right? Complex numbers and their multiplicative norm, right? This is the norm that the modulus of z1 times z2 is modulus of z1 times modulus of z2. You know, the complex numbers form an algebra. They're a vector space. But they're also called a division algebra because everything which is non-zero has an inverse, a multiplicative inverse. So it's a division algebra with a multiplicative norm. There is another division algebra with a multiplicative norm that will give you this. What's it called? Let me show you. So where I'm going is the quaternions. The quaternions are a 4-dimensional real vector space paired with a multiplication. It's not a field because the multiplication is not commutative, right? But it's what's called a division algebra. A division algebra, again, is an algebra which is a ring. Let's see here. Where was I? This one? Yeah. So these are my notes from my number theory course. The links are under the number theory, and the things I'm going to be looking at for the remainder of the lecture, there are PDFs here. So, let's see here, where was I? We'll get back to that. I decided to start with the quaternions. So first of all, the question is, how do you define quaternions? And I don't really want to get into that too much. Basically, you can form them formally as particular 2x2 complex matrices, all right? And so here's an explicit construction of them. They, basically, here's the definition. I mean, this is just a model for them in some sense. Alpha, beta, conjugate of beta with a minus conjugate of alpha. These kind of 2x2 complex matrices, you can call them quote-unquote quaternions. I personally would think of these as a representation of the quaternions, not the quaternions themselves. To me, the quaternions are something more abstract. But anyway, the norm of a quaternion you can just define to be the determinant of this 2x2 complex matrix, which gives you alpha, alpha bar, beta, beta bar, which is alpha bar squared plus beta bar squared, which basically is just the sum of the real components of alpha and beta. So like if alpha was, 1 plus 2i and beta was 3 plus 4i, this would end up being 1 squared plus 2 squared plus 3 squared plus 4 squared. So the norm of a quaternion is naturally the sum of 4 squares. All right? And it's multiplicative because determinants are, property determinants. So the quaternions are, they behave pretty normally. They got distributivity properties. Again, the norm is multiplicative because the determinant's multiplicative. And let me just get to it. Here's the usual notation. So actually, once you have these rules, for example, I times I is minus 1, or j times j is minus 1, or I times j is k, j times I is k, you can take these as the defining conditions for the quaternions. And so, I mean, it's totally reasonable to just say that the quaternions are an algebra H that's formed like this. Where ij equals to k, and jk is equal to I, and ki is equal to j, and I squared equal to j squared equal to k squared equals to minus 1, and ji is equal to minus k, etc. I mean, I think you can collapse all of these into the single relation ijk equals to -1, if I remember right, and that they anti-commute. Anyway, I'm not trying to be minimalistic here. I'm just trying to tell you, we don't really need to use 2x2 complex matrices in principle. You can just define them as a formal system if you wanted to. But, this is from John Stillwell's Elements of Number Theory book, which is pretty concrete. So he wants to actually give students a specific model of something that behaves as the quaternions, right? Anyway, philosophy aside, here's what you could say is 1, I, j, and k. And getting to the real point here, so I can introduce a notation. I can say my quaternion, alpha, has a real part and then an imaginary part. I, j, and k are usually called versors. Don't ask me why. So the real part is just t, whereas the imaginary part, and I just threw in the I, j, and k for the imaginary part here. So you can write alpha as the real part plus the imaginary part. You notice this is a slight digression from our usual imaginary notation in like complex, where the imaginary part is itself real, and we pull the I out separately, right? So it's really the imaginary vector component here in contrast. And anyway, you can define the conjugate to be the real part minus the imaginary part. So basically that just flips I to minus I, j to minus j, k to minus k, just like you might expect. And we can write the norm as the product of alpha and its conjugate. And if alpha is t plus xi plus yj plus ck, then you get t squared plus x squared plus y squared plus c squared. These are, of course, the invention of Hamilton, although I guess this character named Graves did, or Rodriguez, I forget, one of these other long dead 19th century mathematicians invented it a couple years before, or discovered it, depending on your philosophy, or maybe it's both, about 1840. And so this is one of Hamilton's really greatest contributions to mathematics, he thought. And he really did think of it as being a representation of space and time. It has all kinds of metaphysical baggage that comes with it that I don't really care about. Anyway, so getting to the point, what does the product of two quaternions look like? I personally first saw this when I was like an undergraduate. I remember working this out with my brother in the basement of my parents' house and going, whoa, cool, because this single product has the dot product and the cross product all in one foul sweeping construction. So if I take special kinds of quaternions, like ones that have no real part, so just pure imaginary quaternions, they naturally correspond to the vector, right? Like alpha 1 is kind of like the vector x1, comma y1, comma z1. Alpha 2 is basically the vector x2, comma y2, comma z2. And when you multiply them, according to the rules of quaternionic algebra, I squared, j squared, k squared is -1, so there's your dot product. And then the rest of these guys conspire to give you the components of the cross product, which you have by now forgotten, since you didn't take Calc 3 that recently, right? No, you know the cross product. You love it. You say, I never forget the cross product. It'd be like forgetting your first love or something, right? You wouldn't do that. Okay, maybe that's a little much. But they were very important to Hamilton, like really important. Like the last few years of his life he spent trying to write, well, he did write it, and then he died. But his son published this like 500-600 page book on quaternions. But they used to be much more used by, they're very popular. Quaternions play the role that vectors now do for your education. We used to do vector calculus with quaternions. Yeah? Uh-oh. My first love? Math, of course. I don't know. What was my first love? That's a good question. Did that get recorded? Yes, but it wasn't a serious answer. So let's hear. It's not that interesting, really. All right, so alpha 1 equals to t. I would ask Mr. P the same, but I know better. Alpha 1 equals to t1 plus alpha 1 vector. There's no telling what kind of answer I would get. Let's see here. Alpha 1. So if you then take arbitrary quaternions, which have real parts and vector parts, all right, you can. There you go. Graduate students used to get really annoyed. Like I would draw a picture in my notes, and then I would like get a colored pencil out and like shade it in during class, and they'd be like, they get really annoyed. Like, how do you have time to do that? Like, I write fast. But anyway, I'm not sure the relevance. Oh, yes, your color pens. See here. Anyway, so if you multiply two quaternions, you get this formula. Basically, there's the real part, and then there's like the imaginary part, and then there's the real times the imaginary and the real times imaginary from both pieces. This is the one we just calculated in the last slide. It has the cross product and the dot product in it. All right. So anyway, I'm just giving you some like neat formulas for how to multiply quaternions, and anyway, I think it's interesting. But I mean, nothing I'm telling you right now couldn't be told to high school students who were interested, right? It's nothing really that abstract here. If you're just willing to accept there's these things called I, J, and K that square root of -1 and anti-commute, right? That's a little out there. But so is pi. We're just more used to it. I mean, what's pi? How do you define pi? You're like, it's the first positive zero of the function defined by the sum n equals 0 to infinity of x to the 2n over n 2n factorial divided by, no, wait a minute, multiplied by, I forget. I don't know. You can define it as the first positive zero, in terms of the first positive zero of cosine, which is defined in terms of a series if you want. So there's the definition of pi. You're like, well, the pi is the circumference divided by the diameter. But is that really a definition?
It's true for every circle. So.
It's true for every circle, unless the circle happens to not be in flat space.
Well, it's true for everything.
And you just need circle. It's always two-dimensional.
Yeah. What's that? I mean, I can define a circle to be the set of all points that are equidistant from a central point. So if your notion of distance is so limited to just be Euclidean, then sure. Am I talking about that? Yeah, philosophers are like, that's absurd. That's like squaring the circle. It's like, well, yeah. So what? Mathematicians have squared the circle for like a couple hundred years now, I think. Where you guys been? I mean, have you seen the soup norm? The circle's a square, man. The circle's a square, man. Sorry, I digress. So the product of a quaternion. No, see, now I have to explain myself because you. Let's see, what's a soup of soup norm? So like the soup, this thing. Well, you call it max, I guess. The max of f value of x and f value of y, I think, is the thing. So if you look at the set of xy equal to 1, I think, if I remember right, is this the one? I can't remember if this is it, or that might give you a diamond. I can't remember. It's either this or that. I'm now a little fuzzy. I'm really off topic. Thanks, Bradley. This may be.
I think it's the left one.
It's the left one? This one?
Yeah.
Okay. What's that? Oh, that's the one norm. Never mind. So my point is that's a circle with respect to this notion of distance. Yeah. All right. So let's get back to the actual abstract algebra. All right. I'm going on. So alpha bar is the product of t plus alpha, t minus alpha, right? Because that's the quaternionic conjugate. And so when you multiply this, basically these two terms cancel, right? And you got your t squared, and you got minus alpha bar. But the thing is, that has two pieces. It's got minus the dot product of alpha with itself, right? So that minus and that minus conspire to give you a plus alpha dot alpha. And then, of course, the cross product of a vector with itself is 0. That you remember, right? And so there you go. T squared plus alpha dot alpha, which is to say that the norm of a quaternion is t squared plus x squared plus y squared plus z squared. And so once you have a quaternion and you've established that it has a norm and that norm is multiplicative, well, then the 4-square identity is as easy to find as the 2-square identity was at the start of class, right? There's proof of the multiplicativity. Yay. Here's the 4-square identity, which I don't want to write down. So it basically just comes from looking at the norm of q1 equal to the norm of q2 equal to the norm of q1, q2. A norm of q1, a1 squared plus b1 squared plus c1 squared plus d1 squared. A norm of q2, a2 squared plus b2 squared plus c2 squared plus d2 squared equals to multiply these things. And when you multiply these things out, you get that's the real part, the I part, the j part, the k part squared, and of course, there it is. So there's the formula for multiplying the, if you want to multiply the sum of 4 squares and rewrite it as another sum of 4 squares, there's how you do it. So, as it seems to be the case with anything that touches on number theory, Euler did this in the 18th century, 17 something or other. Euler found this, and I forget if this is the one what's his face there did also. No, this is not the So there's a 4 square identity. What good is it? Well, well, I guess to get back to what good it is, yeah, I guess I should stick with this. I'm debating whether or not I should. I mean, ultimately, the 4 square identity allows us to prove this big theorem, which is that any positive integer, all right, any positive integer whatsoever, can be written as the sum of 4 squares. Not necessarily uniquely, but any positive integer you can write as the sum of 4 squares. This can be proved with this 4 square identity and the things which are in this lecture I'm about to go through. Now, one of the main tools towards doing that is this thing called the Hurwitz integers. Hurwitz integers are quaternionic. I mean, this would be quaternionic. This is kind of the analog of like q adjoining the square root of minus 2. Like here's integer linear combinations of quaternions. So it's kind of like a quaternion. It's like an integer lattice inside the quaternions. This is a little bit too sort of spaced out to support a division algorithm. So you have to throw in like halfway points, and that's what's called the Hurwitz integers. So the Hurwitz integers is you've got I, j, k, and these sorts of things. Turns out that has a division algorithm. And the other thing is the norm of things. It's not entirely obvious that the norm of something like this would be an integer, but it is. For somewhat interesting reasons, if you look at an integer linear combination of these elements, like a times this plus b times that plus c times this plus d times that, the norm of it would be this squared plus this squared plus this squared plus this squared. And you go through some rather delicate, well, they're not too delicate, but they're not entirely that obvious arguments. And you can prove that it's an integer because you end up getting that the thing inside the big parentheses here has to be a multiple of 4. So it being a multiple of 4, it cancels out the 4, and you're left with an integer. So in fact, this is a norm in the sense that we've talked about this semester. And this is pretty crucial because Q, an element of the Hurwitz integers with norm an ordinary prime implies that such a Q is also a Hurwitz prime. Just like in the Gaussian integers, if we get the norm of something as a prime, if you have a Gaussian integer and the norm is 13, it implies that that Gaussian integer is a Gaussian prime as well. Right? You can't reduce it. I mean, if you have any in the sense that I think in this, I don't think we're too careful about the distinction between prime and irreducible in number theory. So you got to kind of forget that distinction we've made in here for a second. But let's say that this is an irreducible if that's prime. All right, you can't. In fact, if you factor it into the product of two Hurwitz quaternions, then one or the other of those is a unit. So you get this theorem that if p is a prime in the integers, but it's not a prime in the Hurwitz integers, then it must be that p is the sum of 4 squares. And that those 4 squares are basically these 4 squares have the property that twice them is in the integers, which either means that a and b and c and d are integers or that they're half integers. So that's kind of an interesting thing. We've seen something very similar in the Gaussian integers. I'll talk about that either later today or some other day. I've kind of put the cart before the horse here. I probably should have done the Gaussian integer stuff first. Oh well. I just got carried away with this quaternion stuff, so let me keep going. Another claim, an ordinary prime in the integers which is not a Hurwitz prime is the sum of 4 integer squares. Let's see here. An ordinary prime. So the proof is here. Anyway, let me get to the punchline. Actually, this calculation here is just absolutely beautiful. Not mine, mind you. This is from Stilwell's book, which I'm sure is from somewhere else. But if you have a prime, an ordinary prime, right? And if you have an ordinary prime and it's the, I need to make sure I got the conditions stated here. Just a second. Back it up. So we're assuming what? We're assuming we have something in the Hurwitz integers. It's a sum of A prime, B prime, C prime, and D prime with these I, J, and K, the versors. And basically the thing is the A prime, B prime, C prime, and D prime are like even integers. And then this omega is the, something like, it's got the fractions in that piece. We can make such a decomposition for any alpha in the Hurwitz integers, all right? Now, the thing about this omega is it has the property that it times its conjugate is equal to 1. Now, that may not be entirely obvious, but, well, I guess it is actually pretty obvious. This is the sum of the squares of the real components of this. So that's basically just saying 1/2 squared plus 1/2 squared plus 1/2 squared plus 1/2 squared is equal to 1, which we can all agree with, right? Because if you add a fourth 4 times, you get 1. So this isn't that complicated. So with that in mind, if you have a prime and you factor it, if you have p equals to a squared plus b squared plus c squared plus d squared, where a, b, and c and d are half integers, then we can rewrite this as this. That's just using the quaternionic norm being the quaternion times the conjugate. And then what did I do here? What's my next step? Remember, I assumed that we can rewrite a, b, c, d in terms of that and that. And then I just multiply these. So like omega times omega bar, and this times omega bar, and that omega times all of that. And the thing about this is that this is the number 1, and these, since these are even, and since that's what? That's half. That's like half integers. So you're looking at something even times something that's got halves. The big story here is that what we're looking at in this product right here is again an integer. So you got an integer plus an integer. This whole factor is an integer, and this is by construction is the conjugate of this thing. So that's also an integer. This is an ordinary prime, like in the integers. So what does that mean about these two things? Either one of them or the other of them. I mean, they have to be right. In other words, it's impossible, right? Because you can't factor a prime into a product of two things that are integers and are not just p again. So what that shows is that an ordinary prime p, which is not a Hurwitz prime, is the sum of 4 integer squares. But these arguments are just I think they're just masterful. I mean they're really interesting applications of algebra, abstract algebra, to solve real specific number theory questions. In this case, studying how it is that integers are decomposed into the sums of 4 squares. Let me get to the punchline here. So it is the case that the quaternions, the Hurwitz integers form a unique factorization domain, but you got to be careful because it's not commutative, so you got to talk about left and right divisors. It's a drag. It's not fun. It's kind of complicated, but it's also doable. There's a Bezout identity. There's the prime divisor property. If you have a real prime, and if it does, but the prime, be careful. The prime divisor property holds for ordinary primes, not necessarily for Hurwitz primes. So if you have P a prime divisor of alpha beta, then either P divides alpha or P divides beta. It's not quite the prime divisor property because again, it's just for the real primes inside the Hurwitz integers. So this is kind of the usual thing with quaternions. Quaternions are very, very close to the usual commutative stuff, but there's just something somewhere that fails you. Quaternions are kind of almost commutative. They're just a little bit past it. Anyway, getting to the four-square theorem, you need this thing called Lagrange's lemma. Lagrange's lemma says the following. If you have P in an odd prime, right? P equals to 2n plus 1, then there exists L and M integers such that P divides the sum of 1 plus L squared plus M squared. All right. So the proof of this is not really that important to us. I'm going to go on. But so there's the four-square theorem. Every integer is the sum of four squares. You can find a squared plus b squared plus c squared plus d squared equal to n for any n in the positive integers. Now, I mean, some of these are dumb, right? Like 1. 1 squared plus 0 squared plus 0 plus 0 squared. Okay, yeah, like yay. Or 2, 1 squared plus 1 squared plus 0. Okay, yeah. Or 3, well, we were stopped, but I mean, I think 1 to 4 is pretty easy, right? Although even at 4, you see the non-uniqueness, right? Because 4 is 1 squared plus 1 squared plus 1 squared plus 1 squared plus 1 squared, but it's also 2 squared plus 0 squared plus 0 squared plus 0 squared, so it's not unique. But notice this. If n is equal to ab, right? If a and b are composite, so if n is a composite number, so it's say it's the product of two things. Well, if you can write a as the sum of four squares, and if you can write b as the sum of four squares, then we're done. Because we got the four-square identity, which says that you can take the product of two sums of four squares and rewrite it as a sum of yet another particular four squares, albeit ugly and complicated, as we saw earlier, right? So what this means then is if you can prove the four-square identity for primes, you're done. In fact, if you can prove it for odd primes, you're done, because we've already got the even prime, the only even prime, right there. 2 is so lonely. They say 1 is the loneliest number, but I think they're wrong, I guess 1's not even prime, so what does it have to say? But anyway. Sorry, I will try to limit the number of 3 Dog Night references for the remainder of this lecture. Where did I go? Where did, oh man. Oh yes, here we are. So, it suffices then to prove it for an odd prime. So basically, if you, we've showed that P divides m squared plus L squared plus 1 on the previous page. And then you can factor this using the Hurwitz quaternions. Like m squared plus L squared plus 1 factors to L minus 1 minus Li minus Mj, 1 plus Li plus Mj. Therefore, P divides this or that, all right? And so if P divides either this or that, that means that either one or the other of them is a multiple of the prime, because again, the prime divisor property for the Hurwitz integer holds for ordinary primes, and consequently, let's see here, but you can't have 1 over P, where P is an odd prime, be part of a Hurwitz integer, right? Like 1 over P, where P is 3 or 5 or whatever, that's not something that you can get equal to a Hurwitz prime, which has at most like fractions of a half. So this can't happen which shows you that there does not exist such a gamma, which shows you what? That shows you that P is not a Hurwitz prime. So P is a prime, but not a Hurwitz prime. So in other words, that means that it can be written as a sum of 4 squares, as I was showing you on the other page. But there you go. That proves that any integer, because of the 4 square identity, can be written as a sum of 4 squares. So a little bit of history, and then I'll dive back into the quadratic stuff again. Okay. So the 2 square identity has a pretty ancient. I mean, Diophantus, 200 AD, knew it. This guy, 1593, De Moivre, Coates, Euler, Gauss, all these dudes did stuff with it in the 17th or 18th century. And then Dedekind, he's the one who did it. In fact, most of the arguments you see in this course, one way or another, they're from Dedekind. What he did on algebraic integers is still what we're doing. 4 square identity, it started with Euler. Rodriguez, that's the other guy. And 1840, Hamilton, 1843. Both basically found the quaternions. And Hurwitz integers were Hurwitz integers basically sit inside the quaternions, and we can use those to study the 4 square problem. The Gaussian integers sit inside the complex numbers, and we can use those to study quadratic problems. All right, I have a lot more to say about that to you guys. Maybe not. I'll say some of those things today, but not all of them. So here's the result I was mentioning. A norm division algebra, is a vector space over the reals paired with a multiplication which satisfies this multiplicative property. So there's a famous theorem by Hurwitz that only for n equals to 1, 2, 4, and 8 does there exist an n square identity. So it's not obvious that it fails for 16. I mean, this is not the easiest thing to prove. There's a proof of this at the end of your linear algebra book if you took it with me last semester, and Curtis, the last section in that book proves it. It's about 3 pages of gory linear algebra. It's accessible, it just would take an hour of your time. And so the only norm division algebras are up to isomorphism, the reals, the complexes, and the quaternions. Oh, and also the octonions. And the octonions are, what do you lose with octonions? If I remember right. Associativity, yes. They're still power associative, though. In fact, the Cayley numbers are power associatives. Cayley numbers are the things that are above the octonions. Well, I mean, the things above the octonions is Sidonians, and it goes on. But so let's go back to the start. Oops, too far. Pell's equation. So Pell's equation is x squared minus ny squared equals to 1. By the way, this isn't actually Pell's equation. Euler called it Pell's equation, but apparently that was a misnomer. It's older than that. But Pell's equation, like, we can analyze Pell's equation using some of the number systems that we've discovered, invented. Anyway, we've studied them this semester. So you're looking for integer solutions to something like this, right? X squared minus ny squared equals to 1, right? This is what's there, right? And here we're thinking n is a positive number, right? So n equals to 2 or 3, etc., right? So think about this. If you look at the integers, right? Adjoin the square root of n. So in other words, you're looking at things like a plus b square root of n, such that a and b are integers, right? If you're willing to work with such things, think about this. You can factor this as x plus n squared, goodness gracious, x plus y square root of n, x minus y square root of n, right? And in fact, you can define the norm, I mean, we've done this, of a plus b root n. What was it? We usually put n equal to d, don't we? But this is what? A squared minus nb squared, is that right? And we put this out here to be safe. And the thing about this is, how does it work? I mean, we got the norm of zw, we get what? Norm z, norm w, right? So what does this say? If you have a solution to Pell's equation, what else do you get? Oh, the side and diagonal numbers, forget about those. Oh my goodness. You can solve this thing with rational calculations, but yowzers. Golly. Oh man. Yuck. All right, here we go. This is the one I want. Claim. If if xi, yi solves, and I'm just looking at Pell's equation with n equals to 2 for a second here, all right? But there's really nothing special about putting, I mean, you could replace the 2 with an n here, and this calculation goes through just the same. So I have a solution to Pell's equation, right? X squared minus 2y squared equal to 1. Then I'm claiming x3 is also a solution if we set x3 equals to x2, x2, x1, x2 plus 2, y1, y2. And let me write that out in a little bit more detail. Make sure you guys see what I'm saying here. So we're claiming that we have, you know, x1 squared minus 2 y1 squared equals to 1, and x2 squared minus 2y2 squared equals to 1, right? And then we're using the solution x1, y1, and x2, y2 to construct a third solution to Pell's equation. The third solution is this. It's formed by x1 times x2 plus 2 times y1, y2, and x1, y2 plus y1. Can you see what that is in terms of the number system z adjoining the square root of 2? Like, what is that to this? Where's that x3 coming from? Like, if you take x1, right? Look at x1 plus y1 root n, right? And you have x2 plus y2 root n. What happens when you multiply these? See, that is exactly what is x3, and this is what I'm calling y3. And the claim is that x3 squared minus n times y3 squared is also equal to 1. Why is that? It's because if the norm of the norm of x1, why is my real question is, why is the norm of x1 plus y1 times root 2 equal to 1?
The product of it.
I mean, this being 1 is exactly the same as it being a solution to Pell's equation, actually, because the norm here is Pell's equation, right? I mean, the norm is Pell's expression, and then this equal to 1 is Pell's equation. But the thing is, this is, I mean, if you think about the norm of this times this, well, it's the norm of this times the norm of that. If the norm of this is 1 and the norm of that is 1, then the norm of the product is 1, which is to say that when you multiply these two numbers and z adjoin the square root of 2, you get another solution to Pell's equation. So studying Pell's equation is assisted in the same way that the study of, like, sum of 4 squares is assisted by quaternions. I mean, these abstract numbers, I mean, yes, they're great tools for you guys to learn how to use and apply definitions and write proofs and all that stuff that's important for math majors, but these are also objects which were invented to study specific problems in number theory, right? Now, the proof I give here is not as insightful, right? Here I just prove it with just raw, gory algebra, which is dumb. But it's what my number theory students needed to see when I taught this course. Well, you can agree or disagree, I don't know. What do you think, Jess? Yeah. The cool thing about this, right, is if you find one solution to Pell's equation, right? Like, for example, with n equals to 2, it's pretty easy to see that 3 comma 2 is a solution, right? So 3 squared minus 2 times 2 squared is equal to 9 minus 8, which is equal to 1, right? So x1, you can set x1, y1, the solution pair, to be 3 comma 2. That's a solution to Pell's equation with n equal to 2. What the theorem says is if you just multiply them as elements of, if you view your solutions not as pairs x comma of integers, but instead as numbers in the algebraic integers, z adjoin the square root of 2, then you can, like, multiply it by itself, for example, right? Just take the 3, 2 times 3, 2, you get 17, 12 as a solution. Well, that starts to be less obvious, right? 17 squared minus 2 times 12 squared is 1. 289 minus 288 is 1, right? Obviously, duh. But, you could take 1712 and look at it as 17 plus 12 times root 2 and multiply it by itself and generate another solution. 17 squared plus 2 times 12 squared plus, let's see here, 24 times 17, I guess. Is square root of 2. So in other words, 289, is that right, 289? 17 squared, 289, am I right? Plus 288. And 24 times 17, whatever that is. This is another solution to Pell's equation. So how many solutions are there to Pell's equation? Infinitely many. And what is the significance of solutions? What is the significance of Pell's equation to you guys? This is a ring, right? Z adjoin square root of 2 is a ring. It's an infinite ring, right? What are its units? We've shown that the units are the elements with norm 1. In the language of number theory, those are the solution to Pell's equation. There are infinitely many. It's vastly different when you change that 2 to the square root of minus 2. Those are called imaginary quadratic fields. They're much simpler. They have at most, there are most 8 numbers, I believe. Well, there's more to say here about quadratic number fields and so forth, and I guess I'm out of time, so I'll shut up. But tomorrow I'll go over the solution to the homework you're supposed to turn in today. And then Friday is yours. You can ask me whatever you want. We have a test Monday, as you know. And then the remainder of next week, I'll talk about the rest of this story, which is basically just going to be a brief tour of the algebraic number theory, the abstract algebra and the number theory course that I taught, which I think will make sense to you guys now since you know a little bit about abstract algebra. So thanks, guys.